All right, where did I put that? Good grief. I can't find anything in here. I don't know. Ah, crap. Today we're going to talk about the Russian peasant algorithm. It's a method of multiplying two numbers together, and I think it's kind of cool, personally, but it has the added benefit of being a way that we can implement mechanically to multiply together binary numbers on the computer. Okay, so here's what we do. We say we're going to multiply 25 times 8. We have this in two columns, and in the first column we'll go down and we'll divide by 2 without the remainder. So like 25, we see it's an odd number. Take away the 1, it's 24. Divide that by 2, it's 12. Okay, divide 12 by 2, it's 6. Divide 6 by 2, it's 3. 3 is an odd number. Throw away the 1, make it a 2. Divide 2 by 2, and that's 1. Okay. Now, parallel to this, okay, we take our number 8 that we're multiplying the 25 by, and we double it. Okay, 8 times 2 is 16, times 2 is 32, times 2 is 64, times 2 is 128. Okay, now we go over here, and whenever we have an odd number in the column, we put we carry over the number of the other column. So 25 is odd, so we bring over the 8. 3 is odd, so we bring over the 24. 1 is odd, so we bring over the 128. And we have these 3 numbers in this column now. Then we just add them together, and we get 200. And 200, hey, that is 25 times 8. Now, I'm going to do this again, doing 25 times 5. But I noticed something here, that I have a pattern, okay, that I only need to do this halving operation once, and I said, this is the first one, it was odd, the second one it was even, the third one it was even, the fourth one it was odd, the fifth one it was odd. And when I bring my 5 down and double it, 5, 10, 20, 40, 80, okay, I then just bring over the ones that were odd, so 5, 40, 80, add those together, it's 125, which is again correct. And I like this because cutting things in half is easy, and doubling things are easy. Doing that, you know, it can kind of free up your brain, provided that you remember stuff and write stuff down, and you know how to add numbers. So this is a way of multiplying numbers together, and all you have to know how to do is to double and to halve and to add. But the question might arise, why does this work? Okay, let's do a derivation of this. First, let's take the number 25. 25 is 2 times 12 plus 1. Okay, now take the 12. 12 is 2 times 6 plus 0. 6 is 2 times 3 plus 0. 3 is 2 times 1 plus 1. And then 1 is 2 times 0 plus 1. Again, we're just applying the division algorithm here. Okay, now I want to take that away, and what I want to do, okay, I'm going to take this expression for 1 and resubstitute it here, then take what I get here and resubstitute that for 3, and then take what I get for the 6 now, resubstitute that for the 6 here, and then take what I get then for the 12 and resubstitute it up here. Okay, so I can get my my 25 represented using only 2's in it. And so 3 is 2 times 0 plus 1 plus 1. 6 is 2 times 2 times 2 times 0 plus 1 plus 1 plus 0. 12 is 2 times, and so forth, right? I'm just resubstituting in, and it gets kind of wacky. But when I multiply it back all together and keeping the power and keeping it in terms of powers of 2, I get 25 is equal to 2 to the 4th plus 2 to the 3rd plus 0 plus 0 plus 1. Okay. Now, if I take any quantity q times this, times 25, I distribute this out, and so it'll be 2 to the 4th times q, at 2 to the 3rd times q, plus 0 times q, plus 0 times q, plus 1 times q. Okay, so see, when I take 2 to a power times q, I am doubling that. Okay, so I'm doubling here q 4 times. Here I'm doubling q 3 times, and so forth. And so this just gives me, you know, what I need. And notice this q here, it doesn't necessarily have to be just an integer. Okay, it can be a floating point number, a decimal number. So I think that's kind of makes this even more cool, that the only thing we really need right here is the only thing we need this sort of expression for is the first number. Okay, but I'll show you more here in a second. Okay, when we start talking about powers of 2, we think about binary numbers. And so what I'm doing in the process of my 25 when I have my 25 and when I'm cutting it in half, I am creating a binary expansion for it. And every time there's an odd, I'll put down a 1, and when it's even, I put down a 0. And so this sort, you know, this the right hand side corresponds to the top, and as we go to the left, we're going down our column. Okay, and so here I have 5. I didn't do 5 in binary before, but when I express the decimal 5 in the binary, it's 101. Okay, and I'm rendering it now because I want to show you how this plays out on a computer. Okay, we start out 25 and 5. Okay, when we cut something in half, we just shift it over. Okay, you know, the dividing by 2 and getting rid of the remainder corresponds to just moving everything 1 towards the right. Okay, so my 1 0 0 0 1 becomes 1 1 0 0. When I cut it in half, it becomes 1 1 0. When I cut it in half, it becomes 1 1. When I cut it in half, it becomes 1. This is known as a shift operation, shift to the right. Now, I take my 5 over here. When I double it in its binary expansion, I just shift it over 1 towards the left. And so, and put a 0 in the spot that I've opened up. And so 101 becomes 101 0. 1010 becomes 10100. And so you just keep stuffing zeros in here. Like when you multiply something by 10, you just put a 0 here. You're multiplying by 2, you just put a 0 in. Mechanically, it corresponds to an operation in a computer register called a shift. Okay, and so we're shifting one direction over here, we're shifting the other direction over here, and then we do as we did before here. Yeah, I put that on the wrong line. This should be 101 anyway, not that it's a big deal, but then it's just a matter of adding these binary numbers together. Okay, and I get that binary, my answer is 1111101. And over here I'm checking my work because, as you might notice, I'm kind of iffy with arithmetic. And so it's 1 plus 0 plus 4 plus 8 plus 16 plus 32 plus 64. And that gives me the 125, just as it ought to be. Yeah, who is it? No, I'm not doing anything. Come on in.